The last real topic that we have to consider is that of kinetic theory, which is essentially going to be relating the speed of molecules in, say, a container to their temperature. Just some basic assumptions is that we have a large number of molecules and they're moving in random directions with a whole bunch of speeds, so it's actually kind of hard to track maybe just an individual atom. So here we might have an atom going in that direction with that speed, here we might have one going a lot faster in that direction, and kind of so on and so forth, slower, different directions. We'll say that on average they're far apart and they're not going to have any gravitational attraction, so they only interact when they're colliding, and when they do so, collisions are perfectly elastic, and what that means is that their kinetic energy is going to be conserved. Now, this isn't quite true for the real world, however it's close enough for this class. Now, I'll kind of skim through this derivation fairly quickly. First, we're going to remember some impulse from Physics 201. F delta t is equal to the change in momentum, so change in m delta, or delta mv. Kind of rewrite this guy to say here, divided by delta t, and then say if we consider a particle moving in that direction, it's going to bounce off of a wall. Now it's moving backwards perfectly elastically with the same velocity, so the change in momentum is going to be 2 times the mass and the velocity. We'll just consider the x direction for right now. And then the change in time is going to be essentially distance is equal to rate times time. So we can rewrite this expression as such. And then we say, okay, well, this is just for one molecule. If we do this for all molecules, so n now is going to be the number of molecules, we can write the force to be as such. But this is just the x direction, and we do have 3 directions to consider. So what we do is we kind of say, hey, what we'll do is we'll look at the average speed right here. That's what that little bar means. Is we're just going to essentially divide by 3, and so now we have the force in all 3 directions. Pressure is simply force divided by area, so take that guy and plug it on in down here. Realize that the area times the length is going to be related to the volume. And lastly, we can take this and rewrite it as such. Then recall the ideal gas law in this form. If we were to say divide both sides by n, so divide that side by n, divide that side by n, you can kind of see that PV over n is going to be equal to kT. And this little creature right here, that looks like our old friend 1/2 mv squared, so it's going to be the kinetic energy. And actually, since this is an average velocity, it's going to be the average kinetic energy. So what we can kind of say at the end of the day is equation 13.8, that the average kinetic energy is going to be directly proportional to the temperature, which is also going to say, hey, temperature is actually a measure of the velocity, of the energy of the gas. Now, very rarely are we going to be talking about the kinetic energy of the gas. We're really much more so interested in the speed. So of course you can rewrite this and take the square root of the average speed to get this speed right here, the average speed of a gas as a function of the temperature, where this is actually has a special name. It's called the root mean square speed, which is slightly different than the average speed. Actually, this is going to weight the speeds more preferentially towards the higher speed. If the distribution was a perfect bell curve, which is what you're most familiar with, in that case the average speed, the peak speed, is also going to be the RMS speed. But in this case, the distribution of speeds is not quite, as you'll see, not quite a bell curve, as you'll see in the next couple of slides here. Keep in mind that this temperature must be in Kelvin, and this is going to be the Boltzmann constant. Make sure that you're pretty familiar and comfortable with this equation, because this is the equation that you're more likely than not going to be using. Now, just kind of a qualitative look at what's going on here. If we have, say, a whole bunch of particles in a box, and these guys, as I've said, are going to be moving at different velocities in different directions. If I kind of looked at the relative number of molecules and looked at their speed, we'd see a big, huge distribution, which, as I've said, is not going to be a nice, pretty bell curve. There's a whole bunch of statistical mechanics going on in the background here that you don't care about, but the distribution is going to more or less look like this. It's called a Maxwell distribution, and essentially the most probable distribution right here, the peak speed, is going to be slightly different than this RMS speed that we talked about on the last slide. And kind of as I mentioned, it's going to be preferentially weighted towards some of the higher velocities. If we were to increase the temperature of the gas, say from 0 degrees Celsius to 37 degrees Celsius, what's going to happen is we're going to have some speeding up on the high end here, and that's going to shift the most probable speed up. It's also going to shift the RMS speed up, which is kind of what you'd expect. Higher temperature, higher gas speeds. Now we've been talking about gases for quite a bit. We started off by talking about solids, so let's kind of come and wrap it all up with what we call a phase diagram. Essentially, if we were to say, you know what, I'm going to plot pressure along the y-axis and temperature along this axis, let me talk about whether I'm in a solid phase, a liquid phase, or the gaseous phase. Let's just kind of start off with that 1 atmosphere, which is what we're kind of familiar with. And here we're looking at water. So at 1 atmosphere, we know that if it's fairly cold, water is going to be in the solid ice form. At 0 degrees Celsius, it's going to melt. So going from a solid to a liquid is called melting. If I were to be going in reverse, then essentially I'd be calling it freezing. Now if we were to increase the temperature, we're all in the liquid phase of water, all the way up to 100 degrees Celsius. And essentially, if we're talking about on a molecular level, what's going on here is the molecules are going faster and faster and faster. When it hits 100 degrees Celsius, we're going to boil, and we're going to have the gaseous phase of water. Now the interesting thing is hey, let's consider, what if we were at a much lower pressure? Well, we could actually go straight from the solid phase into the vapor phase simply because we're at a lower pressure, and this is called sublimation. Going in the reverse direction would be called deposition. One interesting point right here is going to be this point right here, where we can have solid, liquid, and vapor phase all existing at the same time. This critical point right here is the point where the gas, where it will always be in some gaseous phase. No amount of pressure will be able to keep this. Will be able to keep water from entering the liquid phase. Now let's take a look at this liquid to gas exchange just a little bit closer here. We all know that in these dry winters here that we can leave, say, an open container with some water in it, and the water is going to evaporate. So we've kind of seen this. Now if we were to consider water molecules at the very bottom of, or at the very top of this container here, and we say that hey, there's also going to be some water molecules up in the air here, kind of what's happening when something evaporates is these guys all have some speed associated with them. They're constantly moving, and actually the speeds are going to be different. So I've kind of drawn this guy here to have a much faster speed. What's going on here is this guy has just enough energy through collisions to pop off the surface here, and actually what's going to happen is the kinetic energy of this liquid is going to become slightly less, and so it's actually a cooling process. If we were to blow air across this, we'd call it a swamp cooler. Now if we were to say, hey, well, suppose I've got a water molecule right here, and it bounces into the wall, it loses just enough energy such that it goes plop into the water, we would call that condensation. And if the rate at which the water molecules are evaporating or condensing are the same, then we'd say that this is just an equilibrium. In this case, we would say that the water vapor is said to be saturated, so this up here is going to be saturated. And if we were to measure the pressure, then we would say that the pressure of the gas is going to be the saturated vapor pressure. So if we took a look at how this saturated vapor pressure is going to change with temperature, we would expect as it gets hotter out, the saturated vapor pressure is going to increase with temperature, and that really is what happens if we looked at temperature and pressure. As the temperature increases, so also does the saturated vapor pressure. So what this is kind of saying is it gets hot, humid, and muggy, or as it gets hotter, it gets more muggy. And kind of a more practical application, we would say that a liquid is going to boil when its saturated vapor pressure equals the external pressure. In this case, it's going to be the pressure of the atmosphere. So here we have, say, atmospheric pressure kind of pressing down on that. So 1 atmosphere pushing down on this liquid is going to boil when the saturated vapor pressure equals the atmospheric pressure. And essentially, if I were to, say, decrease my atmospheric pressure, if I were to go hiking in Colorado, then this liquid is going to boil at a much lower pressure. And so if you want to cook pasta, then you would have to cook it for longer. Also, I could actually make this liquid boil by putting it in a vacuum chamber and sucking out all the air, and I could make this beaker of glass boil without heating it at all in a laboratory. Now we can relate this vapor pressure to something that we're more familiar with, which is relative humidity. I have to say that first we can talk about partial pressure. If we consider a mixture of gases, say nitrogen, oxygen, and water vapor, partial pressure is going to be the pressure of each if it was the only gas present. And the partial pressure of water in air can be as low as 0 and as high as the saturated vapor pressure at that temperature. If I were to look at relative humidity, it's going to be the partial pressure of water divided by the saturated vapor pressure multiplied by, of course, 100%. And really what we're kind of looking at is up here is going to be how much water is there, and then down here it's how much water vapor can the air hold at that temperature. Now we all know that when the humidity is high, it's going to feel muggy and terrible. Essentially what's kind of going on here is there's a lot of water in the air, so it's hard for water to evaporate off of your skin, cooling you off into the air because the air is already saturated. We can talk about dew point, which is essentially you take a parcel of air and you cool it down to some temperature at which it would be saturated. And if the temperature goes below that dew point, then we're going to get dew, fog, or even possibly rain. The last concept to talk about for liquids, is also true for gases, is going to be diffusion, and essentially all diffusion says is if I were to take a drop of food coloring and put it into some water, I don't have to stir it. On the molecular level, we're looking at collisions, where here we have a whole bunch of water molecules, and these guys are in motion, and they're going to be bumping into each other, and essentially they're going to spread this drop of dye through collisions, so I don't even need to stir it. This process is called diffusion, where we're going from regions of high concentrations to regions of low concentrations, and kind of conceptually the temperature is going to matter. If I was at a higher temperature, then these molecules would be moving faster, they'd be colliding faster, and we would reach this state much quicker than, say, a cooler glass of water. We can talk about the rate of diffusion if we were to say, hey, let me just take kind of a cylinder here, because it's easier to look at, and look at the flow through this distance delta x. It's going to be related to the area. So the flow rate is just going to be the area divided by how long of a chunk we're looking at. As the flow rate is going to be related to kind of the concentrations over here and over here. More concentrations means it's going to happen faster. So the flow rate is related to the difference in concentrations, as well as some diffusion constant, which really depends on the medium as well as the temperature. So here we can have diffusion from air, water, and say blood, so on and so forth. As in 201, I'll just kind of page through the summary slides and let you take any notes that you may want.